Hi, in this video, I'm going to give you some tips on curve fitting and polynomial fit. Suppose that you wish to construct a mathematical model that fit your measurement point. We let x to be the independent variable, y as the dependent variable, and finally, we let delta y as the error of the measurement. The model is given by a function f of the independent variable x. Here, P is a set of parameters that characterize the function f. For example, a straight line is described by f of x equals to m times x plus c. Also, the parameters of a straight line are m, which is the gradient, and c, which is the y-intercept. The main idea of curve fitting is to search the optimum parameters of a curve, P0, such that the corresponding chi-squared value is the most minimum. Here, the chi-squared is given as the squared sum of the weighted difference of the measured value and the predicted value. In the formula, y is the measured value obtained from the experimental data, while f of x is the predicted value obtained from the model curve. Also, the summation is done over the entire measurement point. Note that n is the total number of measurement points. Of course, the closer the measurement points, y, to the curve of f of x, the better the quality of the fit. Here, the smaller the difference between y and f of x, the smaller the value of chi-squared, which implies a better fit. Now, let us focus on fitting a polynomial curve of any degree to the measurements data. This curve fitting technique only applies to polynomial curve described by the following function. Here, we define a0, a1, a2, and so on as the parameters of the polynomial curve. Note that k is the degree of the polynomial. Also, the polynomial has k plus 1 number of parameters. Suppose that we have collected our experimental data and we wish to fit a polynomial curve to the data. So now, our objective is to find the optimum parameter values, P0, that give the best fit with the lowest chi-squared value. To begin, we define two matrices x and y as follows. The number of rows of matrix X and matrix Y is equal to the number of measurement data points, n. However, the number of columns of matrix X is equal to the number of polynomial parameters. Note also that matrix Y only has one column. Intuitively, matrix Y is the list of measured quantities obtained from the measurements data. Here, all first column elements of matrix X is equal to 1. Next, the second column of matrix X is the list of the independent variable x to the power of 1. The third column of matrix X is the list of the independent variable x to the power of 2. And then, we repeat adding the columns of matrix X until x to the power of k, which is the degree of the polynomial. Finally, we define matrix M as follows. The elements of matrix M is simply the element of matrix X divided by the corresponding measurement error, delta y to the power of 2. Once we have prepared the matrices X, Y, and M, we can simply calculate the optimum parameters P0 using the following formula. Here, the symbol M with the superscript T indicates the transpose of matrix M. From the formula expression, we also require to calculate the inverse of a matrix. This can be easily done using Excel or various other math tools. The parameter errors are given by the square root of the diagonal elements of the covariance matrix. Here, the covariance matrix is given by the inverse of the matrix multiplication of transpose M and X. For example, suppose that we wish to fit the measurement data given in the table to a straight line model. Again, a straight line model is a 1-degree polynomial. Here, we define the parameter matrix of the straight line consisting of A0 and A1. Also, A0 is the y-intercept and A1 is the gradient of the straight line. So now, suppose that the measurement data is already inserted into the Excel sheet. And our focus now is to build matrix X. So we begin evaluating the first element of matrix X, which is given by X to the power of 0. And finally, we have X to the power of 1. And then we build matrix X by dragging the first row until the end of our measurement data. Next, we move our focus to matrix M. So evaluating the first element of matrix M, which is simply the element of matrix X divided by the error of y to the power of 2. And then we proceed building matrix M by dragging the first row until the end of our measurement data. And then now we evaluate the parameters by copying the Excel formula and then we replace M with the corresponding range for matrix M, and we replace X with the corresponding range for matrix X, and finally we replace Y with the corresponding values of Y. So for a straight line we have two parameters, and the y-intercept is given by minus 14.3723 and the gradient of the straight line is 2.63. To evaluate the error of the parameters, first we need to evaluate the covariance matrix. To build the covariance matrix, we copy the Excel formula given and we replace M with the corresponding range for matrix M as well as X. The parameter errors are given by the square root of the diagonal elements of the covariance matrix. So for the y-intercept, the parameter error is given by square root of the first diagonal element, and the error of the gradient of the straight line is given by the square root of the second diagonal element.